I want you to picture a single fiber optic cable, just, a standard cable.
Yeah.
Now imagine taking the entire global internet traffic, like every video stream, every email, every single financial transaction happening on Earth right now, compressing all of that into a single pulse of light and firing it across a city in 1 second.
And doing all of that not with some massive warehouse-sized room full of servers, but with one single microscopic chip.
Right, which just sounds like science fiction. I mean, it sounds totally made up. But that is an actual mind-bending statistic from a 2022 experiment at the Technical University of Denmark.
Yeah, it really happened.
They transmitted 1.84 petabits of data per second over a 7.9-kilometer cable, and they did it using just one photonic chip.
Which is just, I mean, it's staggering to even think about the math there.
It really is. So welcome to today's deep dive. We are exploring the invisible physical backbone that is making speeds like that possible for you and me. We've got a massive stack of sources today, spanning, financial market reports, semiconductor deep dives, technical encyclopedias.
All the heavy reading.
Exactly. And our mission today is to understand this fundamental bottleneck happening right now. We're looking at how the totally insatiable demand for AI computing is forcing this massive infrastructural shift from traditional electronics over to photonics.
Because, frankly, we are hitting the hard physical limits of traditional computing. I mean, every time you prompt an AI to write a report or generate an image, you're kicking off this microscopic chain reaction that is quite literally actively breaking the global hardware supply chain.
Breaching it completely.
Yeah. The industry is being forced to just abandon the electron in favor of the photon, and it's triggering this modern-day gold rush for a super obscure material called indium phosphide.
Okay, so before we get into why all these tech giants are fighting tooth and nail over this obscure material, I feel like we have to grasp the sheer scale of what AI is demanding from our hardware right now. Because, for decades, our entire digital world has been built on just pushing electrons around.
Right, pushing them through copper to do math and move data.
Yeah. But electrons have a pretty fatal flaw when you scale them up to this level.
Oh, absolutely. Moving electrons over copper wires creates resistance. And as any basic physics class will tell you, resistance creates heat.
Lots of heat.
So much heat. It is slow, and it's incredibly power hungry. When you have these giant AI models doing their training or inferencing, the servers have to talk to each other constantly. They're passing massive, massive data sets back and forth.
Right.
And if you try to do that with traditional electronics at that scale, the system essentially just melts itself, or it requires a small nuclear reactor just to power the cooling systems.
Which obviously isn't sustainable. Our sources actually point out that a single AI server requires over 10 times the number of optical modules compared to just a standard web server. 10 times.
Yeah, it's a totally different beast.
And there's this quote in the financial reports from the CEO of Lumentum, they're a major optical communications company, that really puts this into perspective. He noted that for just one major cloud provider, the network capacity required to connect just 2 of their AI data center sites is double the total global backbone capacity they built over the entire last decade.
That's just
2 sites. Double a decade's worth of global infrastructure. It's nuts.
Right, and that is exactly the moment an infrastructure upgrade goes from being, a strategic 5-year roadmap to an absolute hair-on-fire emergency.
Yeah, scramble mode.
Because the only way to move that volume of data without creating catastrophic heat is through photonic integrated circuits, or PICs.
Okay, PICs, let's talk about those.
So these chips use optical wavelengths between 850 and 1650 nanometers. And the beauty is, light travels at the speed of light, naturally, and it does so with virtually zero electrical resistance.
Okay, but wait, I have to challenge the premise of this whole crisis here, because we've had fiber optic cables forever, right?
Oh, sure, decades.
And silicon is obviously the undisputed king of computing. I mean, we have these massive multi-billion-dollar foundries churning out silicon chips all over the planet. So why can't we just use silicon to make these light-generating chips? Problem solved, right?
Well, you would think so, but it all comes down to the atomic structure of the material itself. Silicon is what physicists call an indirect bandgap material.
Okay, an indirect bandgap. Let's break down the mechanics of that, because I know silicon photonics is actually heavily used in the industry right now for routing light around a chip.
Yes,
It
exactly.
handles all the passive components with, very low signal loss.
Right, it acts as a fantastic mirror or a pathway. It's
Right.
great for the roads, but it completely fails as an emitter. It cannot be the engine.
Why is that?
Okay, think of an electron's energy like a ball sitting on a shelf. In a direct bandgap material, when the ball rolls off the shelf, it drops straight down.
Okay.
And it releases all of its energy instantly as a flash of pure light. That's a laser. But in silicon, which is an indirect bandgap, that shelf is staggered. It's like a staircase.
Oh, I see.
So the ball has to bounce sideways first. And that sideways bounce releases its kinetic energy as heat, not light. So an indirect bandgap material simply cannot efficiently emit a laser photon just by applying electricity. It just gets hot.
So silicon can be the roads and the highways for the light, but it can't actually be the engine generating it. You need an entirely different atomic structure to natively generate that laser on the chip.
Exactly.
Yeah.
And the entire AI industry has settled on for this is indium phosphide.
Indium phosphide.
Yeah, because its direct bandgap structure allows for near 100% photoelectric conversion efficiency.
Wow. 100%.
Almost, yeah. The ball drops straight down every single time. And furthermore, it naturally generates light at exactly 1310 and 1550 nanometers.
Which are the magic numbers.
Right, those happen to be the golden wavelengths for fiber optic communication. Light at those specific frequencies travels through glass with the absolute minimum amount of signal degradation.
Which explains why indium phosphide has, like, practically overnight become the most coveted material on Earth. The supply-demand imbalance detailed in these financial reports we looked at is just brutal.
It's a bloodbath.
I mean, in early 2025, a standard 2-inch optical communication-grade indium phosphide wafer cost about $800. By April 2026, that same wafer surged to between $2,300 and $2,500.
And if you need it right now, spot prices for urgent orders are currently crossing $3,000.
That is insane.
Well, and the industry is desperately trying to transition to high-end 6-inch substrates, right? Because you get better manufacturing scale. You can etch vastly more photonic chips onto a 6-inch wafer.
Naturally, yeah. Bigger canvas.
But the pricing there has skyrocketed from $1,400 to $5,000. That is a 250% increase, and it is entirely driven by this transition in AI network speeds.
And the math of this shortage is really fascinating when you dig into it, because data centers are actively upgrading their optical modules right now from the 800G standard to the new 1.6T standard.
Right, going from 800 gigabits per second to 1.6 terabits per second.
Exactly. But the raw material requirement doesn't scale linearly. A 1.6T module requires about 2.7 to 2.8 times more indium phosphide than an 800G module. So the faster we want these AI clusters to think, the faster we drain the physical supply of the material.
And the projections for 2026 show global demand hitting somewhere between 2.6 and 3.0 million wafers. However, the global effective production capacity is severely bottlenecked.
Right.
They can only pump out about 600,000 to 750,000 wafers.
Okay, so we are looking at a supply gap of over 70%.
Yeah.
For every 4 wafers the tech industry desperately wants to buy, only 1 actually exists in reality.
And to make matters worse, the production of this material is controlled by an extreme oligopoly.
Yeah.
I mean, over 90% of global indium phosphide production belongs to just 3 companies.
What?
Just 3. Japan's Sumitomo controls about 43% of the market. Then you have US-based AXT with 35%, and Japan's JX Nippon Mining and Metals holds about 13%.
Where is China in all this? They usually dominate hardware manufacturing.
Interestingly, despite their massive overall manufacturing might, China accounts for less than 5% of the high-end 6-inch production right now.
That's wild. It's as if, like, the whole world suddenly decided to build giant skyscrapers at the exact same time, but we just realized only 3 small quarries on Earth know how to make the structural steel, and they're completely book solid until 2027.
That's a perfect analogy. And to push that quarry analogy further, you can't just throw venture capital at those quarries to make them dig faster.
Right, you can't just build a new factory in a month.
Not at all. The environment required to grow these indium phosphide crystals is incredibly hostile, and it's heavily, heavily patented. Just one single production line costs over $175 million to build.
Jeez.
But the real choke point, the thing slowing everyone down, is the core equipment, the MOCVD machines.
Okay, let's explain MOCVD, because that stands for Metal Organic Chemical Vapor Deposition, which sounds like impenetrable scientific jargon, but mechanically it's actually a fascinating process.
It really is. Basically, MOCVD is essentially atomic spray painting.
Atomic spray painting, I love that.
Yeah, so they have to vaporize highly volatile metal organic compounds and literally spray them atom by atom onto a heated substrate. And this all happens inside an extreme, high-temperature, high-pressure vacuum chamber.
So they're literally growing a crystal layer by layer from scratch.
Exactly. And the machines that perform this atomic spray painting, they take 1 to 2 years just to be built and delivered to a factory.
So even if you have the money, you're waiting 2 years for the printer.
And even once you finally have the machines bolted to the floor, ramping up the yield is a complete nightmare.
Because it has to be flawless, right?
Right. Getting a high percentage of usable wafers without any microscopic defects takes 3 to 5 years of pure trial and error for the engineers on the floor. A single microscopic flaw in the crystal lattice ruins the entire photonic chip.
So even if a tech giant writes a blank check today, like right now, they aren't seeing new high-yield wafers until maybe 2028 or 2029.
Exactly. Since you cannot just wish new factories into existence to solve this 70% supply gap, the companies that actually build these optical modules are facing a brutal bottleneck.
Yeah.
And this constraint is actively crowning the winners and losers on Wall Street right now.
Let's look at that corporate battlefield, because Lumentum is completely pulling away from the pack here. Their fiscal Q4 2026 earnings were just staggering. They posted $1.01 billion in revenue.
Which is incredible.
Yeah, it represents 109% year-over-year growth. They crossed 50% non-GAAP gross margins, way ahead of schedule, and they hit their $1.25 billion Q1 target early.
But, the strategic puzzle here is how they achieve this while explicitly stating in their earnings call that their key pump lasers are completely sold out.
Yeah, that part is wild.
Right. They're expecting a 4-fold increase in shipments over the coming quarters,
Right.
but they simply cannot manufacture them fast enough.
I have to say, I am genuinely confused by that math. If you are starved for raw indium phosphide and you literally have no inventory left to sell, how are you projecting massive revenue and margin growth for the next quarter? Where does the growth even come from if you are physically out of the material?
It's a great question, and the answer is, if you can't sell more chips, you have to sell higher value systems.
Oh, okay.
Lumentum is aggressively shifting their architecture into what the industry calls CPO, that's co-packaged optics, and NPO, which is near-packaged optics.
Okay, we should definitely break down the geography of the server motherboard to understand what is actually being packaged here, because traditionally the optical transceiver sits all the way at the edge of the server rack, right?
Yes.
The silicon GPU does its intense math, sends an electrical signal all the way across the copper traces of the motherboard to the edge, and then that edge component turns the electrical signal into light to send it down the fiber cable.
Exactly. And moving those electrons across just those few inches of motherboard creates massive heat. It wastes a ton of power, and it introduces latency.
Right. Co-packaged optics takes that optical light engine and physically moves it off the edge of the board. It integrates it directly next to the GPU on the exact same substrate.
Oh, wow.
Yeah, so you are trading some incredibly complex packaging challenges up front to gain massive power efficiency and speed on the back end.
So by integrating the optics directly alongside the silicon, Lumentum isn't just selling a raw laser chip for a few dollars anymore. Our sources show they actually just secured their first order for an external light source module, or ELS, for delivery in 2027.
Right. They are moving up the food chain. Instead of selling a basic component, they are selling a highly integrated, sophisticated module for a massive premium.
Which allows them to grow revenue and margins exponentially, even if the raw number of indium phosphide wafers they consume stays relatively flat.
Exactly. And, they are also aggressively securing their future supply.
Yeah.
Lumentum is actually converting a massive fabrication plant they acquired in Greensboro, North Carolina.
Ooh. Yeah, they are switching it from older gallium arsenide production over to indium phosphide, aiming for revenue by early 2028. And they're signing major long-term supply deals with AXT to lock down that precious raw substrate.
You really see the divergence in strategy when you look at their primary rival, Coherent. Lumentum's market cap surged past $48 billion, officially overtaking Coherent. Lumentum is growing 4 times faster, and they expanded operating margins by over 1,700 basis points year over year.
And Coherent?
Coherent only managed 140 basis points.
Ouch. Yeah, well, Coherent got caught in the exact manufacturing trap we were discussing with those MOCVD machines and crystal yields.
Yep.
They experienced a super painful 6-month lead time delay in transitioning their internal production from 3-inch to 6-inch indium phosphide wafers.
And the ultimate irony in this corporate battlefield is that while Coherent was waiting to get their 6-inch wafer production sorted out, they actually had to buy optical components from Lumentum just to meet their own customer demand. Right. Your biggest rival becomes your supplier because you missed a critical manufacturing step.
It just highlights how unforgiving the hardware layer of the AI boom really is.
Totally.
But, looking beyond the data center, all of this frantic R&D, all the billions of dollars being poured into making these photonic integrated circuits smaller, hotter, and faster, it's creating these profound spillover effects into completely unrelated industries.
And that is always the most exciting part of massive technological leaps, because tech giants are spending billions to solve the physics of AI speed. Entirely different fields get the trickle-down benefits.
Exactly.
Your next heart monitor or the safety sensors on your car might be vastly improved simply because an AI data center needed to move data faster.
Yeah, and healthcare has seen some of the most fascinating applications of this. Because these photonic chips can manipulate light at a microscopic scale, they can be used to create incredibly sensitive biosensors.
Like the one from Amazec Photonics.
Yes. Amazec developed a photonic sensor for measuring cardiac output and circulating blood volume with sub-millikelvin precision.
Which is just crazy. Measuring blood volume based on temperature fluctuations less than 1,000th of a degree. The accuracy is astonishing.
It really is. And in the surgical suite, there's a company called EFI that developed a device called Optorip. It uses optical sensors to give surgeons greater tissue feeling during minimally invasive surgeries.
Tissue feeling, how does that work?
Well, when a surgeon is using a robotic arm, they traditionally lose the tactile feedback of holding a physical scalpel.
Yeah.
They can't feel the resistance.
Right, it's just a joystick.
Exactly. But by using light to measure microscopic deflections and pressure changes on the surgical instruments, the system can instantly translate that back into force feedback. The surgeon can practically feel tissue resistance through the robotic arm, powered entirely by optical sensors.
That's incredible. And it goes from the operating room straight out to the farm, too.
Yeah.
Agriculture and the food industry are using PICs for non-visible light sensing. But miniaturizing near-infrared spectrometers onto these tiny chips, farmers can analyze the chemical composition of crops instantly.
Right out in the field.
Yeah. They shine near-infrared light on a piece of fruit, analyze the specific wavelengths that bounce back, and detect ripeness, soil quality, or even spot plant diseases in real time. They can even use these tiny chips to analyze the chemical makeup of milk or sort plastics for recycling based purely on their optical signature.
And we also see this massive integration in the automotive sector. Autonomous vehicles rely heavily on LIDAR, which is fundamentally a photonic technology bouncing lasers to map the physical environment.
Right.
But beyond LIDAR, they are embedding PICs alongside fiber Bragg grating sensors to sense pressure, temperature, and vibration.
Now, a fiber Bragg grating is one of those concepts that sounds impenetrable, but it's actually incredibly elegant. It's essentially a microscopic modification etched right inside a fiber optic cable that acts as a highly selective mirror.
Right.
As a car frame bends, or the engine temperature changes, that microscopic grating stretches or compresses. And that tiny physical stretch changes the exact wavelength of light that reflects back down the fiber.
So by reading the specific color of the reflected light, the car's computer knows exactly how much stress or heat a specific component is under.
Instantly.
And it does this with a level of durability that traditional electronics struggle to match, because light isn't affected by electromagnetic interference from, say, the electric motors.
We are really watching a technology fundamentally mature right before our eyes. But it didn't just appear out of nowhere, did it?
No, not at all. Decades of academic groundwork laid the foundation for this exact moment. I mean, back in the 1980s, a researcher at Delft University named Mint Smit invented the arrayed waveguide grating, or AWG.
Okay, an AWG.
Yeah, and an AWG works a bit like a highly advanced prism. It separates different colors of light, so multiple distinct data streams can travel down the exact same fiber optic cable simultaneously without interfering with each other.
Wow, back in the 80s.
Yeah. Brilliant minds have been advancing integrated photonics for 40 years. They were just waiting for a commercial catalyst large enough to achieve massive manufacturing scale.
And the AI boom is obviously that catalyst. It is writing the blank checks that are finally scaling photonics to the masses. When you step back and look at all these sources today, from the indium phosphide bottleneck to Lumentum's co-packaged optics pivot to surgeons feeling tissue through light, it becomes entirely clear that the AI boom isn't just a software revolution.
Not at all.
We are physically rewiring our entire technological backbone. We're abandoning the electron for the photon.
Yeah, the physical constraint of building artificial intelligence is basically forcing humanity to master the manipulation of light on a global industrial scale.
Which leaves us with a final lingering thought for you to take away today. Right now, we are mostly using photons to connect giant AI servers in remote warehouse-sized data centers. But as these photonic integrated circuits get smaller, cheaper, and vastly more power efficient, how long will it be until the personal devices in our pockets, our phones, our laptops, our wearables, abandon electricity entirely and run purely on light?
It's crazy thought.
The age of electronics might quietly be ending right now, making way for the age of photonics. We want to thank you for joining us on this deep dive. Keep exploring, keep questioning, and we'll see you next time.